Hello, ladies and gentlemen, and thank you very much for turning up for this webcast on scaling of musculoskeletal models. We have three small points that I want to take you through before we get to the question and answers session. My name is John Rasmussen, and I am the presenter of this webcast. And next to me is Arne Kies. He is trying to get the technology to work and make sure that everybody has sound. And I also have with me Sylvain Karp, one of our supporters, and he will be helpful in answering questions on the way. In this type of event, you can actually ask questions anytime you like. You don't have to wait until I tell you that you can ask questions. What you do is you go to the bottom part of your screen, and you should be able to find a little panel down there, the one I underline on my screen here. And that little panel has a question mark. If you click the question mark, you will get a question and answers panel. And into that panel, you can type your question at any time during the presentation. Please make sure that before you submit the question, you elect to submit the question to host, presenter, and panelists. That way, everybody here in the room will get your question and can answer it as quickly as possible. If the question is simple and easy, then Sylvain will try to answer it right away online while you're watching. And if we think that the question seems to have any sort of general interest, then we will postpone the answer until the end of the webcast, and then I will take it in the question and answer session there. So I will be going to the first part of the presentation, which is about scaling principles. And what I'm going to go through here is the different scenarios in which you may want to scale musculoskeletal models. One thing that we might want to do is we might want to scale models on a very detailed level, so that we simply want to make every decision about muscle insertion points and length of segments and every other parameter that you can think about in the system. This has actually always been possible because the models we use in Anybody are written in a programming language called AnyScript, and they are completely open. So any user can go into any part of the model and modify the model any way he or she wants to do it. So this is really not very new that this has always been possible. The problem with that type of scaling, of course, is that it is a huge job, and it's very difficult to find the necessary data that you need to modify the existing models to a certain individual. So we're going to be looking at two other types of scaling today, and those are the ones that you see here at the bottom of the screen. Those are scalings on an individual level, such as you would do if you were working, for instance, in sports biomechanics and wanted to model a particular athlete, or if you were working in health science and you wanted to do, say, gait analysis of a particular individual and wanted to get that gait data into a model and do some sort of analysis, musculoskeletal analysis based on that data, and valid for that particular individual. You may also want to do scaling on an overall population level. Say if you're into product designing products like cars or sports equipment or medical devices that are manufactured to fit a cross-section of the population. In that case, you might want to scale your models on a population level to different percentiles of the population. And you may also want the models to fit different populations, say European, Asian, American, and so on. And so you probably will want to do this based on some anthropometric databases. And those are the two types of scaling that I will be addressing today. I'll first look a little bit into how a segment is actually defined in Anybody, and I'm doing that to set the stage for the types of scaling that we can do more or less automatically in the system. Now, if you look at the figure here on the left-hand side, you can see the usual bones and muscles that you see in an Anybody model. And but one of the important things to notice here is that the bone geometries here are really just icing on the cake. They are not actually a representative for the mechanics that goes on inside the body. If we want to represent the mechanics in a more visual way, we could use a different way of displaying the model, like the one that you see on the right-hand side. Here you can see the same segments or bones represented as what they really are in the system, namely a set of mass properties represented by these ellipsoidal potatoes in the middle of the segment, and also a set of points that move in the local reference, or that are fixed to the local reference frame of the segment, and those are the yellow pinheads that you see sticking out of the potato. That's really all that there is to a segment. There's some geometry which is basically the point cloud of these pinheads, and defined in the local coordinate system of the segment. And then there are some mass properties that are represented by the potatoes themselves, and which also have to be scaled so that they can be different between smaller or larger people. So in terms of segments, we have geometry and we have mass properties that have to be scaled. Let's take a look at how muscles are defined. So the next picture, you can see a number of muscles. You see the muscles highlighted here by bulging, and the bulging is actually proportional to the force that we are computing in the muscle. You can see these muscles also have a number of different properties that may depend on the scaling. One is that they have a certain origin and insertion points, which are part of the geometry and are actually the points of the pinheads that you saw on the previous picture. You can also see that muscles are often wrapping over bones, like you see the muscle going over the knee geometry here, and these wrapping surfaces are also geometry in the model. Furthermore, each muscle has a unique strength that may or may not be a fixed number depending on the muscle model that we're using. It can be either a fixed strength or it can be a set of rather complicated data specifying the properties of a hill type muscle model. So there is some strength data involved and there's some geometry data involved in the muscles. And if we sum all of that up, you can see that to be able to scale a musculoskeletal model, we have to be able to scale geometry and mass properties and muscle strength. And the model that you see below is a representation of how it's actually done in the scaling methods that we have implemented. The input is what you have on the left-hand side, and the input is the external geometry of the bones. And that external geometry can be represented in different ways. I'll get back to that a little later. And it is also the mass of either the entire body or the individual segments, and I'll also get back to how we're using that. These two properties we put into a scaling law, and out of the scaling law we get a scaled internal geometry of the bone, so the new locations of all the pinheads, and also a scaled strength of each of the muscles on the different segments. So how are we actually performing the scaling? Well, there is probably infinitely many different ways that you can think about doing geometry scaling. We have taken the most simple approach because we simply didn't have data that would justify doing anything else. So if you think of the number or the points S here that I'm highlighting now, if you think of that as the scaled location of a point on a bone, it could be, for instance, a muscle insertion point, then the way we compute this point is by means of an original position of that point, a nominal position in which it has been measured in a cadaver study or based on an MRI scan or something like that. And then we have a scaling matrix S, and we have a translation T. So you can see that within this model, what we need in order to be able to do a scaling is we need to find out what the scaling matrix S and the translation T is. And actually, in what we are doing here, we are pretty much only using the scaling matrix S. So we are going to look at ways of finding that. So it's obvious that different choices of S and T will lead to different scaling laws. Now we have to form ourselves an opinion about how we can set up a model for how this scaling is going to take place. And the thing that we're going to do here is we're going to observe that most of the segments we have in human bodies are longitudinal in nature. And they're configured such that they have a rigid bone in the middle, and then they have some soft tissue that goes around the bone. And obviously, each segment will have a length which can be given by some sort of external measure. So you can simply take a tape measure and you can measure the length of a given segment in the model. Or in a test subject. And then you can see that we also, in a model like this with concentric circles like this, we also have an external diameter that we need to come up with, and this external diameter could then be given by the total mass. So if we have an idea of the total length and the total mass of the segment, we can also then compute what the total diameter would be. And since we have divided the segment into different types of tissue, as you can see here, it's a bone in the middle and it's some soft tissue around it, then by doing that diameter scaling, we will also be able to make an assessment of how much muscle mass will be available in the segment afterwards. We have tried, actually, in the history of the Anybody project, we have tried various scaling methods. And the one that we have ended up with at the moment, which we think is the best one, is a scaling method that we call the length mass fat scaling. And its model is a little more complicated than what you saw before. It's actually, like you see here on the right-hand side, the little picture here, you can see we still have a bone in the middle, and we have some soft tissue around the bone, which we can think of as muscle. And then we have some additional tissue on the surface here, which we can think of as fat. And so we are dividing this model into three different types of tissue. One of the types of tissue is the type we can call other, and that would be representing bone and cartilage and skin and blood and other things. Then we would have the tissue on the surface, which we could think of as fat, and in between those two we would have muscle tissue. Now, if we think of how much muscle would be available in a model like that, we can say that the ratio of muscle tissue to the total amount of tissue in the segment would be 1 minus the ratio of fat minus the ratio of other tissues. So if we subtract the fat and the other tissues from the model, then what is remaining must be muscle. We have a general estimation that says that the amount of other tissue in the model is 50%. This is obviously a very rough estimate, but it's only a number in the model, and if you don't think that this is true, then you can obviously just go into the model and you can change this number. Now, if we have that idea, then we can say that we can actually scale the strength of the muscles in the segment based on an original strength. So the scale strength, which we can call F, will be based on an original strength, which we can call F0, which is the one that we have here, and then a scaling factor that we can compute based on the model that I just presented to you. Now, if you do the math on this model, you will see that the way we can scale it is by means of two ratios. One is the mass ratio, so the ratio between the segment we want to model and the reference segment, and the other ratio is the length ratio, the relationship between the length of the scale segment and the length of the reference segment. Those two go on either side of the quotient here, and then we are adding also a quotient that is based on the amount of muscle tissue in the scaled segment divided by the amount of muscle tissue in the unscaled segment. And this way we can come up with an estimation for how much what the strength would be in the scaled segment compared to the original segment. So each of the muscles in the body that are attributed to this segment will have their strength scaled by the factor that we are computing here. Now, having set up this idea of how we can scale the geometry of the bones and the strength of the muscles, we can then look at what the scaling pipeline would look like. And I would like to take this from the bottom. We would like to end up eventually with musculoskeletal models like the ones that you see down here at the bottom, that have different sizes and also different strengths that reflect their different sizes. And the way we do that is we take whatever data we have and we send it through the scaling law, and that would then output the models that we want. So what are we putting into the scaling law? Well, obviously, based on what you saw just before, we need to put the segment lengths, the length of each segment in the scaled model. We have to measure that by a tape measure or get it some other way. And we also need the masses of each of those segments. If we put those two numbers for each segment into the scaling law, then the scaling law, based on the math that I showed you just before, will spit out the scaled models like the ones that you see down here. The question is then, how how do we get the subject data? Well, the subject data can basically come from two different sources. It can either come from population data, which we have over here on the left-hand side, and population data could be from digital mannequins, such as Ramses or Jack or Delmia or whatever they're called. Or it could be from some population databases like the CESA database that is available from the Society of Automotive Engineers. And there are some other databases out there that have done population studies. You can also get this the subject data from individual measurements, and that's what we have over here on the other side. We have here the opportunity to do scans or palpations or measure external dimensions or whatever, and then we can get information about a certain individual's measurements, and we can then put those into the scaling law, and we will get a model out of that particular individual. Now, this is how it was done until very recently, but in the latest version of the Anyscript model repository version 7.1 that was released a few months ago, we actually added some new opportunities to put stuff into the scaling pipeline. And I'm going to go through those new opportunities very briefly and show you what they can do. So the things to observe while you're working with scaling in Anybody is that the repository models that we are trying to scale are written in a programming language, and we call this programming language Anyscript. And this means, since it is a programming language, the keyword here is programming language, it means that we can implement the scaling methods that we come up with directly into Anyscript. And so this means that scaling becomes a part of the models and not a part of the software. So the models actually contain their own scaling laws. And so the scaling laws that I have been talking about until now, and which I will continue to talk about, are actually implemented in Anyscript. They are not a part of the Anybody modeling system. The Anybody modeling system simply has the capability of handling these scaling laws as they are defined in the Anyscript models. And this has a lot of advantages for users of the models, because the models are, as many of you will know, they are completely open. They are simply models that are written in a clear text format in a well-documented programming language. So you can open up the models, you can scrutinize them, you can find the scaling laws, and if you want to change something or experiment with a certain scaling law, you can go in and make your modification, and you can load the model again and see what happens. So simply, if you don't like the methods that we have implemented for you, you also have the opportunity to make your own. So we have come up with an extended scaling pipeline. And this figure that you see here is almost the same as I showed you before, except that this has a little more detail. This is the scaling that was available before we released version 7.1 of the repository. And you can see that into our scaling law, in this case, we have to put the joint distances. You can also think of these as the segment lengths. So the distances between the two joints that are typically in each end of the segment. We need to know what that distance is, and then we can put that into the scaling law. Similarly, we need to know what the segment mass is, and we can put that into the scaling law. And then out will come the node coordinates and the muscle strength, as I explained before. However, there is a certain drawback about this, and the drawback is that it's actually quite difficult to measure some of the joint distances, because it's not very easy to measure to the center of a joint, and some of the joints that we are interested in are placed inside the body under a lot of soft tissue, so they are not easily accessible with a tape measure. So what can we do instead? Well, we have now implemented some new features. One is that we have implemented a new scaling law that is based not on joint distances but on bony landmarks. So instead of measuring the joint distances, the user can now measure easily palpatable bony landmarks on a particular subject. So that's one improvement. Another improvement is that we also have now a rough scaling based on population percentile in the system, directly in the system. So you can choose a certain scaling law that is a percentile scaling law, and then you can simply choose between a man and a woman and type in the percentile that you want, and then the scaling law inside the model will take care of the rest. And finally, we have one new opportunity that's coming out that a lot of our users have been playing around with lately, which is called the gate application 2. Now, the gate application 2 is a method for processing marker data into movements in an any-body model. And one of the advantages of using this technology is that the gait application 2 can actually also compute scaling factors for each of the segments. So if you do a gait experiment and you have an adequate marker setup, you can actually use this gait application 2 and you can get the scaling factors out of that, which is very convenient. Right now the gait application 2 is a standalone external application, but this is going to be implemented directly into anybody, hopefully in a not too distant future. And so this will be directly available from inside the system. So now we've come to the part where I'm going to show you how we actually implement this, and I'm also going to show you a brief demo of how it works. And the first thing I want to show you is a little code snippet from a typical main file that is available in the repository. So in the repository, all the models that can be loaded, they are called the applications, and they're pretty much structured the same way, so that inside the main file of an application, you can find a choice of scaling law. In this case, you can see that we have chosen the scaling length, mass, fat law, and so there's a couple of different ones that you can choose from. And we have also chosen to use a file from a directory called the any family. And inside that directory, we have a number of different files that represent different sizes of people. And we have taken a rather general one here, which is called the anyman.any. And that is a file which you can go into and you can modify easily, and you can get out different sizes of people by changing some numbers in that file. This was also how it was done earlier. So now that we have new methods implemented, we also have some new scaling files that are available. Those new scaling files are also in the any family directory, and they're the ones that I have mentioned down here. And you can see they're called the anyman external, which is used for scaling a body model based on bony landmarks rather than segment lengths. Then there's the anyman X percentile and the anywoman X percentile, and as the names indicate, these are used to scale men, respectively women, in terms of population percentiles. So if we take a look at what the anyman external would look like, it actually looks a lot like the previous scaling of files that we had. And you can see the entire file here on the screen. You can see at the top of the file we have a variable called the body mass here, which is currently set to 75 kilograms. And then you can see that all the second masses further down are all functions of what the body mass is. So when you change the body mass, you also automatically scale all the segment masses proportionally to the body mass. Of course, this is a rule that may or may not be true for any given individual you want to model. But fortunately, if you do have information from a particular individual that you have measured, if you do happen to know what that individual's segment mass is, then you can just type in that number here anywhere in the system here. So you just erase the whatever is standing here, the formula that is here in the first place, and then you just type in the number that you know is the correct one. And this is one of the advantages of having a programming language, that you can actually write formulas and mathematical expressions directly into the model. Then you can see down here at the bottom, we have the segment lengths, and these are actually just numbers. We could also have made these a function of the body height that we have up here, but we have chosen not to do that because they actually vary a lot between individuals. You know, some people can have long legs and a short torso, and some can have a long torso and short legs and so on, and they will end up having the same total height. So it's a little more difficult to come up with good numbers that would scale these between individuals. But the difference between the previous file and this one is that what's called the thigh length here is not actually anymore the length between the hip joint center and the knee joint center. It is now the length from the top of the trochanter to the lateral epicondyle. And this means that we are now basing this on measurable lengths that you can measure with a tape measure on the outside of a person, rather than the actual joint-to-joint lengths. So this is the difference with this compared to what we had before. I would also like to show you one of the percentile files that has much the same structure, except that you don't input a height or a body mass in the file. Instead, you input a percentile up here at the top, and that is almost the only number you have to change. There is one more thing you have to do though, and that is that we have a regression function down here, the z function that you can see here, and those regression functions actually depend on the interval of percentiles that you are moving in. So if you're in the middle of the percentile range, say here from 16 to 84%, you have to use the formula in the middle. And if you're at a very low percentile, you have to use the top formula. And if you're at a very high percentile, you have to use the bottom formula. And those are the only two things that you have to change in this file in order to get a certain percentile of a person. So right now I'm going to close down the presentation for just a second, and then I will show you a demo of a standing model with a shoulder back, and we can see what the influence will be of having different sizes of people in the model. So I'm going to close this down, and then I will open up the Anybody Modeling System. And I already have my main file listed on the screen here. And if I go down in the main file a little bit, we come to the part that I was talking about, and the one that I'm highlighting now, namely the choice of scaling. And you can see that I have chosen here the Any Woman EXT percentile. So I have chosen that this is going to be a female model, and that I'm going to scale it based on a population percentile. You can see the EXT here in the middle, that part here, specifies that up here in the scaling law, you have to make sure that you choose a scaling law with the last name of EXT, as I have shown here. So not the scaling length mass fat, but the scaling length mass fat EXT law. This is really important, otherwise you don't get a reasonable result out of this. I just want to, before I load the model, I just want to open up this Any Woman EXT percentile file and see what we have defined in here. And you can see that right now I have defined a 95th percentile female, so this is a rather large female. And I have also, because I've chosen the 95th percentile, I have also chosen the regression that is valid from the interval from 85 to 95 percentile. So with that, I'm going to load the model, which I'm doing now. And it takes just a few seconds because it's a fairly large model of a standing person with several hundreds of muscles. And as soon as it's loaded, I'm going to open up a window so you can see what the model looks like. And it should be here in just a second. So now I can open up my model view here, and I can try to, maybe we should look at it from the back. That's actually the best vantage point for this model. So I'm going to scale this a little bit so you hopefully get a better image. And then I'm going to zoom in like this. And then I'm going to run my study. So I'm going to run the inverse dynamic analysis. And this is going to move just in a second from now. It's going to move a little bit. And the muscles are going to fall into place. And now the system is analyzing the muscle activation that is necessary to carry the shoulder bag that you see in the picture. The mass of the shoulder bag is rather high. It's a heavy shoulder bag with 20 kilograms of mass, and therefore you also see a somewhat asymmetrical pattern of muscle activation over here in the back of the model. And this is typical for that type of asymmetrical model, of course. We also would expect to have an asymmetrical muscle activation pattern. So let us try to investigate the various results that came out of this. So we can go into the model, and we can look in particular at two different sets of data that are interesting in this case. The first output that I would be interested in would be the maximum muscle activation. So this is the percentage of muscle activation compared to maximum voluntary contraction that is necessary for the person to remain standing and to carry this 20 kilogram shoulder bag on one shoulder. And as you can see here on this bar diagram here, we have about 47% muscle activation for this case. And I would like you to remember the 47% as the amount of muscle activation that is necessary for a 95th percentile female, that is a rather large female, to carry the shoulder bag of 20 kilograms. And I would also like to look at one other piece of information, namely the loads on the person's spine. So I'll go into the human model and into the trunk, and I will go into the joints, the lumbar joints that we have here. And then I'm going to find the L4, L5 joints, and inside that I can find constraints, and I can find reaction forces, and I can plot the reaction forces, the net reaction forces in the different joints. Remember, these reaction forces are taking the muscle actions into consideration. So these are very, and it's also a very well validated spine model that we're using. So I have a good confidence that these numbers would be reasonably accurate. And you can see that the compression force, which is the green bar, is at almost exactly 1,300 Newton in this model. So we should remember that for the 95th percentile female, we have 1,300 Newton in the spine, and we have a muscle activation of 47%. Now, I'm going to try to change the model back to a 5th percentile female, so a very small female. And while I do that, you can think about whether you think that this is going to give smaller or bigger loads in the small female than we have in the large female. So I'm going to go into my scaling file again, and I'm going to change the 95th percentile to a 5th percentile. And then I'm going to select the corresponding regression law here. And I'm going to load the model again. And we should now get a small female instead of the large female that we had before. So we'll just give the model a few seconds to load, and it should be ready to do the analysis. And you should be able to see as soon as the picture appears, you should be able to see that this model is considerably smaller than the one that we had before. So when we run the inverse dynamic analysis, we are going to get a model that looks like this. And maybe you remember that the head of the model was almost level with the top of the window before, and now you can see that the model is considerably smaller than it was before. And again, please consider whether you think that the muscle activation and the joint loads are bigger or smaller on the small female carrying the same load compared to what it was on the large female. Now the analysis is finished, and you can see the muscle activation pattern here on the small female. And if I take my results window over here again, we can first look at the maximum muscle activity. And you can see that the maximum muscle activity now is 49%. It was 47 before. So there's actually a rather small difference in muscle activation between the small and the large female. And the reason for that is that there are several things in play here. Of course, the small female has weaker muscles than the large female had. But the small female also has a smaller body mass to begin with. And also, because of the scaling of the model, the point of application of force from the shoulder bag is actually closer to the center line of the small female than it is to the large female. So you can see that when we do these types of scaling, there's a lot of different factors that are coming into play. Now, what about the forces in the lumbar spine then? Are we expecting that they should be smaller or larger for the small female? Well, if we go down and plot the number, we can get something like this. And you can see here that the value is now about 1,350. So the compression in the small female spine is actually about 50 Newton higher than it was in the large female spine. So it does look like that because of the smaller moment arms of the spinal muscles. It's probably that which is playing a role here. The small female carrying the same load will have a higher compression load on her spine, and of course her spine will be smaller and will not be able to sustain as much load as the spine of the large female. So comparatively, the small female will have a higher load from carrying the same weight compared to the large female. So I'm going to go back to the presentation again, and I just have a few remarks that I want to make before we end. So you can see that we have implemented the scaling as rather simple formulas directly into the models. And we have based these formulas on simple physical and physiological principles. This is what you could call a simple solution to a very complicated problem. And I should probably right now admit that if you do measurements on anthropometrical measurements on a cross-section of the population, you will get a very complicated pattern of variation between the different people that you measure. And this is something that we have to take into account in future work. And we know from previous experiences that we have that it is really important to include also the age and the gender in the strength assessments that we do, and not only in the size assessments. So we need to come up with some regression formulas that will take age and gender into account as well. Finally, I would like to direct you to some online resources. The Anybody Modeling System is available from anybodytech.com. You can get a free demo license there, and you can actually try out the stuff that I have just shown you. There's also a tutorial available from that website, which is, I believe, is not yet included in the software, but you can view it online on the website. The whole documentation is copied on the website, and there's a scaling tutorial that you can go into, and you can see how all this is done. You can also go to the Anybody Research Project, which is at anybody.aau.dk. AAU is Aalborg University. And you can find there the public domain library of the body models, and also the various applications, including the shoulder bag example that I just showed you. And you can also find references to a lot of different publications, and some of these are about scaling. So with that, I would just like to thank you very much. We'll take a brief break, just probably 10 or 20 seconds to get the questions collected, and then I'll start answering some of the questions. Thank you.